Slater transition state. Okay, so let's start with the first argument. So we know that usually the most conventional implementation of time-dependent DFT follows the so-called Casida-like implementation. So we have this large omega matrix which must be diagonalized, usually with Davidson algorithm. And this is actually the implementation which is at the moment available with ADF. When very large systems are considered, you know, Davidson algorithm is very efficient to extract eigenvalues and eigenvectors. However, this algorithm is a bottleneck when we need many eigenvalues and eigenvectors. So if you are interested in another wide part of the energy spectrum, with the Davidson algorithm, it is not probably the best choice. So, since we experienced this problem about the Davidson algorithm, we have developed a new algorithm which was inspired by our previous work on photoionization, which we played with the TDDFT algorithm, and we have implemented this algorithm, and we have already some application on metal clusters. And if you are interested in the algorithm, this is the paper. So it has been just published in Journal of Chemical Physics this summer. The first author is Oscar Baseggio, who just is finishing his PhD under my supervision here in Trieste. Okay, so of course Casida is not the only possible implementation. There are many other algorithms. So just to mention, this is a little bit of literature on other different algorithms should you be interested. So in order to introduce the new algorithm, it is convenient to start with the general linear response theory for TDDFT. So we know that if you are interested in the density which is induced by an external time-dependent field, this can be at least formally written as a dielectric susceptibility of the interactive systems with integration with the external potential, which this is usually, for example, an external dipole oscillating field where omega is the frequency. Of course, this is rather formal because this object, which is the dielectric susceptibility of the interactive system, is not easily accessible. These are some references which are important for linear response theory should you be interested in more fundamental problems. So, time-dependent DFT is invoked in this case, so we know that we can obtain the same density, the induced density, provided we use other objects in this integral. This is the dielectric susceptibility of the non-interactive system, so the so-called CONSHAM, non-interacting electrons, and this is a kind of effective external field. So, which is very convenient, this expression, because we know this, both these objects. So, the effective external field is actually the sum of the dipole, which is oscillating, plus two terms which comes from the response of the electrons to the external field. So you see, we induced a density, and this density creates a electrostatic field. So this integral is the electrostatic potential, of this density. Instead, this is the effect of the induced density on the exchange correlation potential. And this object is the so-called exchange correlation kernel. As usual in DFT, we don't know this object, but we can have some practical approximation. One is the so-called adiabatic LDA. So this object is just the derivative of the local density approximation exchange correlation potential with respect to the density, and is local in space. This other object, which is the CONSHAM dielectric susceptibility, is actually known from basic theory. This is the expression you can find on this references that I showed before. So you see this object can be expressed as a double sum on occupied and virtual or unoccupied Kohn-Sham orbitals, and we have this expression. So actually, all the things which enter this expression are molecular orbitals, orbital energy, which are the Kohn-Sham eigenvalue. Then we have the frequency of the external field, and then we have this small infinitesimal, which is actually introduced in order to have this adiabatic switching on of the external potential, because we need that the system is in the ground state in the past. So it is necessary to introduce this convergence factor in order to integrate. Okay, so then we have an expression from the effective potential, we have an explicit expression for the electric susceptibility, and then we have a kind of linear problem, because the potential depends linearly on the susceptibility, and this is expressed by the kernel, this relationship. On the other hand, the density depends on the effective potential via the dielectric susceptibility of the Kohn-Sham system. So if we solve all these equations with respect to the density, we obtain this response equation. So this response equation is actually one possible manifestation of time-dependent DFT. You see, it is quite different with respect to the Casida equation. And why this equation is very interesting? Because this equation is an equation for the density, for the induced density. So a very effective possibility is to express this equation using the basis set, which is the auxiliary basis set, which is used for the fitting of the density. We know that in ADF, this auxiliary basis set is employed to fit the electron density, which is very efficient then to calculate the Hartree part of the Hamiltonian, but we can use also this set to represent this equation. This is very convenient because I remind you that in Casida formulation, the dimension of the matrix is the product of occupied times virtual orbitals, which is usually a very large number. In this case, the dimension of the equation is the dimension or at maximum of the fitting set, but even lower because we can select the fitting set. So this equation is much smaller with respect to Casida density matrix formulation. So actually, up to now, we have seen that what we can calculate with this equation is the induced density. And actually, if we have the induced density, we have also simply by integration for a coordinate, this Q means X, Y, or Z, one of the three electric dipole components. So we can obtain easily all the components of the polarizability tensor, and from the average trace of the polarizability tensor, we can extract the imaginary part and then the spectrum, because it is well known that from linear response theory in general, that another possibility is to calculate the spectrum is to extract it from the imaginary part of the polarizability. So in our algorithm, if we calculate this induced density, then we obtain the polarizability, which is a complex quantity, and therefore from the imaginary part we obtain the spectrum. So of course, in this case, we have to fix the frequency, so we can calculate the spectrum simply calculated by point. So we solve the equation for each different frequency which are interested for. Of course, actually the spectrum is not a continuous spectrum, but a line spectrum. So it is convenient to use a frequency which is not only the real part of the frequency, which is actually the frequency of the photon, of the light, but also to introduce a small imaginary part of the frequency of our radiation, because in this case, the spectrum is no more a spectrum by lines, but it is already convoluted. So the spectrum that we obtain at the end is a convoluted spectrum by a Lorentzian, and this imaginary part of the frequency is related with the width of the Lorentzian function. So now the problem is now recast to this, to calculate this, to solve this equation. So this is actually a system of linear equation. The only problem is that we have represented the objects as matrix elements with respect to the fitting set. And so this is the equation written in linear algebra formally. Where is the problem? Actually, okay, we have the overlap matrix, for example, but we have to calculate this matrix. If we do not use any approximation, the calculation of this M matrix would be very time-consuming and not competitive. However, we have introduced in our algorithm some approximation, so it is very easy, not very easily, but I mean very efficiently calculated. So where is the problem? So why it is so time-consuming in principle? It is very time-consuming because the dielectric function should be calculated with this double sum on all occupied and virtual orbitals. And of course, in principle, this would be an infinite sum, so it is not very easy to deal with this object, actually. But the key idea of the new algorithm is that we can obtain formally the same double summation, changing the indexes of this algorithm, so of this double sum, sorry. So instead to sum on occupied and virtual orbital, we can sum here on the interval of this energy, excitation energy axis, and if we divide, we discretize this energy axis, we have in each interval, you see we have discretized, so we have this interval 1, interval 2. Within this interval, we will have some difference of these eigenvalues, because you know that the Kohn-Sham eigenvalues enter this expression only as differences, not as separate eigenvalue. So we can change this sum with this double sum, so we sum first on all the intervals, and then we sum all the differences which lie in a particular intervals. And of course, formally, the sum will be the same, so at the end, the result is the same. But why is this interesting? Because if these intervals are rather narrow, we can say that all these energy differences are very close each other, and then this this factor, which is this lambda, is constant within the intervals. So in this respect, we can extract this factor outside the first sum, and we obtain this expression. So if we look at this expression, this is very convenient, because actually we see that in this way we have we can calculate this object as a linear combination of metrics which are constant with respect to the frequency, so they are all the same for all the frequency which we are interested. The only thing which changes is this coefficient. So we obtain this matrix simply doing a linear combination of metrics which are independent by frequency, and the frequency appears only in this coefficient. So this is the key idea of our new algorithm, and which makes it so efficient. Of course, this is an approximation because we have to discretize its energy. Okay, so in this way, it is rather easy to represent this matrix. So now I will not go into the details because there are many algebra steps, but I mean, the idea is actually that also this M matrix is actually a linear combination of matrices which are rather small and independent by the frequency, and only the coefficients change with the frequency. So the end, with this scheme, the M matrix is calculated at each photon energy as a linear combination of G matrices with a given coefficient. So in this way, the calculation of the dielectric susceptibility is very fast, and of course we have introduced the approximation of the imaginary broadening and then of the energy discretization. So there are some technical details, just how to build all the matrix elements. Actually, we have to say that most of these integrals are already present in the ADF, so we just extract them from the proper routines. So only one new matrix has had to be calculated by new, but just with numerical integration, which is also very easy in ADF. And so when we have this equation, we solve this equation. This, of course, is a linear system of algebraic equations. So this has been already written in a parallel code, totally parallelized using a scalar pack library, which is very efficient for linear algebra. And then from the B vector, which is actually the solution of this equation, then the polarizability and then the spectrum can be calculated. Okay, so this furnishes the spectrum. I want to say, of course, this is also some technical, but that using this modified Sternheimer approach, we can also go beyond this. So from this solution, we can also consider the first order perturbation of the orbitals, and therefore the induced density, and also the coefficient of the CI expansion. So we have all the same information that we can also obtain from the Casida analysis, because you know that also in the Casida formulation, at the end, from the eigenvector of the omega matrix, we can have a representation of the excited state in terms of one electron excited configuration. And we have the same description also with this algorithm. So nothing is lost with respect to Casida formulation. Okay, this is another technical detail which allows to calculate more accurately the polarizability, but it is not very important here. We can just say that from the imaginary part of the polarizability, all the absorption spectrum is obtained, and from the imaginary part of the density matrix, we can do all the analysis of one electron excited configuration, which is the result of the Casida analysis, but also, for example, the transition contribution map, which is also another way to analyze the excited state, which has been suggested by Häkkinen a couple of years ago in this paper. Okay, so I just show some results on small system, just for example to start with the hydrogen molecule. This is the absorption spectrum calculated from the imaginary part of the polarizability. So these circles, this is the transition, these circles here are the ADF results. Actually, this is the ADF from Casida. This is the convolution with the Lorentzian, with these circles, and these curves which are colored are different calculations with the new algorithm. Why different calculation? Because since we use the density fitting basis set, we did different choices of the fitting set. So for example, we used only 2 S function and we have this, or 4 S function in the fitting set, and we already converge. So you see that hydrogen, we can converge only with 4 auxiliary basis function for the density. Actually, if you look at the default fitting set of hydrogen in ADF, it is of 39 functions. So you see that you actually can reduce drastically this fitting for the TDDFT part. Of course, these are necessary in the self-consistent field part of the ADF, but in the TDDFT part, you can strongly reduce this number. So this is another test we did on the real part of the polarizability, and you see that also in this case, these circles are obtained by ADF, this line with the new algorithm, and you see that also in this case, you have a perfect match. Okay, I show very quickly also other tests we have done. This is sodium dimer. Also, you see a perfect agreement between ADF, which is this line, and the new algorithm. This is gold dimer, which is another molecule which is very interesting for us because we are interested to do the application on very large gold clusters. You see, also in this case, of course, here we have some disagreement, but this is also because we wanted to reduce very drastically the fitting set, because we wanted to have a fitting set which is very small, but also rather accurate. So we reduced from 249 to 44 functions. So you see much less functions, but the maximum error is only 0.2 EV, which is actually not so, I mean, it is okay, rather acceptable error. Of course, we can improve if we improve the fitting set, but just to see an application on our system, this was a compromise. So here there are some applications. So this is a gold nanowire. This is a larger system, and this is an example of a plasmon. So you see here this is the result obtained by ADF. So you see these are the discrete line. This is in black is the line which is obtained by convolution of ADF, and this is in blue our new algorithm. So you see that there is actually a rather good agreement between IDF and our approximated algorithm. This is an analysis of the induced density. This is gold 86, so it is a nanowire which is rather long. So we see already the plasmon in this system. You see this is the induced density calculated at this energy. So it is a typical dipole shape. And this is the contribution, the TICI analysis. So from this plot, you can analyze the nature of the plasmon. Actually, this is a two-dimension plot. Here you have the energy of the occupied orbitals, and here you have the energy of the virtual orbital. So this has been done at 2.35, which is this maximum, and you see that actually the strong contribution is given by this spot. This spot corresponds to excitation from the S band of gold, which is here, to in the bound state, to this S band also with some P contribution of gold. So if we analyze the contribution, this is the analysis of the plasma. This is another cluster. It is gold 147, but this is icosahedral cluster, so the shape is more spherical. So it is, less expanded in one direction, so the plasmon is less evident, but you see that you have again the dipole shape of the induced density here in the plasmon, but the analysis is a little bit different because you see that here the S band is not so important. Here we have most of the transition come from the D band, which is a little bit deeper in gold. So you see here it is deeper than S. So we have another situation in which also the D band of gold is important, and this is well known because we know that plasmon is quenched by the screening caused by the D band of gold. Okay, so we have also some other analysis in the new algorithm. For example, the plasmon analysis by the scaling factor, which has been suggested by Bernadotte, Evers, and Jacob in this paper, which is a very interesting work on plasmons in molecules. So we have used their idea to actually check if a transition is a plasmon or is a conventional transition. This can be done just playing with this scaling factor and looking at the shape of the plasma of the spectrum. Of course, in this paper, the analysis is more complete because not only the spectrum must be considered, but actually all the eigenvalues. But this is, I mean, a simplified version of this plasmons in molecules analysis, which can be also very useful to give an attribution of this. Okay, this is a real application of the new algorithm. This is on a gold cluster with different ligands. So what we have found that actually the nature of the ligands is very important for the optical absorption of gold clusters, and actually we have seen that playing with the ligand nature, we can even introduce a kind of rebirth of the plasma, because you see here the gold cluster is 30 gold, consists of 30 gold atoms, but the ligands are different. We have t-Butyl, phenyl, and nitrophenyl ligands. You see that going in this series, this is the ADF calculation with this dashed line, and this is the new algorithm. You see with ADF we cannot go to very high energy because we have the bottleneck of the Davidson. Instead, with the new algorithm we can go without any problem even to higher energy. And what is very important is that the new algorithm, you see that actually going in this series of cluster, we have the appearance of this strong absorption, which is very evident for the comparison. And this is quite interesting as an application. Okay, so we can conclude that saying that the density matrix Casida is not practical to treat plasmons in big metal clusters, since we need too many roots. We have developed a new algorithm which can solve this problem, and is already implemented in ADF code, which is not yet distributed, but it will be in the next release. Not in the next one, maybe, but I mean in a future release. This is the paper, then you can see all the details of the implementation, and we have done some application on metal clusters. So we can see, actually I didn't tell, but this cluster is not symmetric at all, so I mean this is very time consuming, but we think that with this method we can treat a system which contain about 1,000 atoms. So we are using, I mean, we are trying to calculate this kind of clusters at the moment on some big computer. Now we can shift to the second part of my seminar. So I will show some general statement about how to describe core electron excitations, and in particular NEXAFS spectra with density functional theory, but also by TDDFT, so the extension to treat core electron excitation. We will show some very simple example, but which contain most of the physics. So we will review some titanium tetrachloride spectra. I will just underline the importance of the exchange correlation functional choice, and that we can actually use two different methods according to the edge we are interested. So if we are interested in K edge, so excitation of 1s core electrons, it is better to use DFT with the Slater scheme that I will describe later. But if we go to L edge, so excitation of 2p core electrons, so time-dependent DFT will be the choice of election. And then I show some application on larger systems like adsorbed molecules, for example. So first of all, a very fast description of the spectroscopy. NEXAFS spectroscopy consists in the absorption fine structure around the absorption edge of the specific atomic spaces, because you know that every core state has a particular ionization energy, so you can identify different core states even in very complex systems. So this is the physics. So you have the photon, a core electron is kicked off from its orbital, and it can reach some unoccupied virtual orbital or states. So this is the physics. So this is the appearance, how the spectrum appears. So you have usually rather sharp excitations up to the ionization potential. These are very informative about the electronic structure of the system near the absorbing center. And then beyond the ionization potential, we have very broad structures which are called shape resonance. So we actually are not interested in this phenomena. We are more interested in this, so in the excitation to unoccupied electronic states which are bound. Here the states are not bound, are scattering states. These are bound states. Okay, so of course the fine structure corresponds to transition of core electron to unoccupied virtual state. So we have the electric dipole selection rules, but we have to consider that the initial orbital is a core orbital, so it keeps usually its atomic nature orbital, so we can use the atomic actually electric dipole selection rule. So if we start from a K edge, our first initial orbital is an S orbital, so on dipole selection rule, the only P final states will give contribution to the intensity, while if we start from the L edge, so from 2P core orbitals, then both S and D contribution of the virtual orbitals will be important to fix, to identify the intensity of the transition. Okay, so now which are the tools that we have? Of course, we have the density functional theory and the Kohn-Sham method, but we know that actually this method can be used only for the ground state. So if we solve this equation, the Kohn-Sham equation, we obtain actually the ground state density. And we know that excited states are beyond the Kohn-Sham validity. So this is well known from the basic theory. However, we know that at least from a pragmatic point of view, already Slater had proposed many decades ago a method which is called a transition state method, which is very efficient and practical to calculate the absorption spectrum from core electron. The scheme of Slater consists to calculate to do a SCF procedure of Kohn-Sham equation with a so-called transition state configuration. It means that we take half an electron from the initial state and we put it in the final state, and we go to convergence with SCF, and from the eigenvalues obtained with this configuration, from the difference between eigenvalues, we obtain the excitation energy, and calculating this is the electric dipole transition moment between initial and final orbital, we obtain the intensity. Actually, the original prescription was to put half an electron in the final state. However, if we use SCF with ionic transition state configuration, it means that we don't need to put any electron in the final virtual state, but only to reduce of half an electron the initial orbital, and this is the much easier because you can converge very easily on this configuration. It is not easy instead to converge with the SEF procedure on this configuration with half an electron on the virtual orbital. And of course, in this case, the relaxation of the core orbital is included, and you cannot calculate a spectrum with this method. Actually, it is still, I mean, it is very pragmatic. I have already said it is not. It is not correct from a formal point of view because Kohn-Sham theory is restricted to the ground state. However, it works very properly. It works properly for K, so excitation from 1s atomic orbitals. On the other hand, it is possible to do the things in a correct way, so it means use TDDFT for the description of the excited state. And in this case, usually one has this omega, the formulation of Casida, so this is the omega matrix. So the problem is recast to the diagonalization of the matrix. So these are the score of the excitation energies, and from these eigenvectors, the intensity can be obtained. So this is the definition of the omega matrix, of the coupling matrix. And okay, solving this equation, we have the spectrum. Actually, this is practical for the valence, but not so much for the core. For the core states. Why? Because also in this case, we in the implementation, which is usually done, like for example in ADF, the Davidson algorithm is used, and the Davidson algorithm to diagonalize omega matrix is useful only if we need the lower energy part of the spectrum. But core excitations are very high in the spectrum, so Davidson algorithm is not good for this problem. So, okay, this is just a remark that, of course, the exchange correlation potential and functional are very important in TDDFT in particular, and in particular the asymptotic behavior of the exchange part is quite important. So this is this so-called Coulomb tail at large distances. And usually this is not supported by most popular exchange correlation potential. So this is why in our method, usually in our application, we use this AB94 potential, which is actually a potential, a model potential which has been developed in the group of Barents, and supports this tail, and is rather accurate and cheap for TDDFT calculation. So I have already actually told you that a core excitation are too high in energy, and actually these in principle are coupled with the continuum. So this so the problem to solve the core electron with TDDFT is not easy because of these two problems. So essentially because they are very high in the energy. So how can we solve this problem? So this solution has been already proposed by our groups many years ago. So this is the reference if you are interested. And actually this feature to treat core electron excitation is already implemented in ADF. So you can use already this scheme if you have ADF. So the idea is very simple. The omega matrix is this, and if you look at the index runs on pairs of occupied virtual. No, so I is a occupied orbital, and A is a virtual orbital, and J and B is the same. J is occupied and B is virtual. Sigma and tau are the spin. We do not have spin flip, so sigma is the spin of both I and A. So in practical, the pairs IA and JB span all the one-hole, one-particle space, so you have all the configurations in the original omega matrix, but what we can do is just to reduce the run of the indexes which are connected with occupied orbitals, which are I and J, only 2 core orbitals. So what happens? So if this is the complete omega matrix on all the pairs, then if we restrict only to core orbitals, so these are the rows and the columns which correspond to I and J being the core orbitals, so the omega matrix is reduced, and we actually have to diagonalize this smaller matrix. So if we are interested in the core electron excitation, we excite only the core electrons, and the omega matrix can be reduced, and then we can use the Davidson algorithm on this smaller matrix, and now the core excitation will be the lower part of the eigenvalues of this reduced matrix. Okay, so this is the idea. Now I show a simple example. So let's try to treat titanium tetrachloride, and in particular the 2p excitation, with CONSHAM or Slater, if you prefer, and with the TDDFT. So in this case, I will show you that for 2p excitation, TDDFT is necessary, because if you use CONSHAM or Slater, the result will be completely wrong. Okay, so this is the result. So this is the NEXAFS of 2p, the experiment of 2p excitation of titanium tetrachloride. So you see you have these two excitation in the L3 edge, and if you calculate the TDDFT excitation, you obtain these two transitions, which of course are shifted with respect to the absolute energy, but are in good agreement with respect to the intensity. On the other hand, if you try to do it without TDDFT, so for example by CONSHAM or as later, there will be no difference at all, you obtain two transitions with roughly the same intensity, which is completely wrong with the experiment. So you see that you have to do with TDDFT to obtain a good description of the spectrum. So why happened this? So why we have this? So it is so wrong, the CONSHAM and the Slater. So because we have to see why we have two transitions. So we have to see a little bit better which is the electronic structure of titanium tetrachloride. So we are doing excitation of 2p electrons. So these 2p electrons can go on the 3d orbitals of titanium, which are formally empty, and they are split by the tetrahedral point group symmetry into sets. So we have the E orbital and the T2 orbital. So this is the reason that we have two different transitions which are split by this. So at CONSHAM level, this description is given by a simple excited configuration. So I put here one electron, or I put here one electron. On the other hand, if I describe this excitation at TDDFT level, I have the omega matrix elements. I have also extra diagonal elements. So actually these two configurations are mixed in TDDFT, and so this mixing can be rather strong and very important to fix the intensity. In fact, if you look at the description, of course, at the CONSHAM level, the description is, as I already told you, 100%. There is no mixing at all. While in TDDFT, you see that the first transition is actually contributed mainly with this excitation, but there is also a little bit of the other configuration. So this the opposite is for the other excitation. So you see that at the end, this mixing of configuration actually solves the problem of the intensity. So in this case, that it is in a very good agreement with the experiment. Okay, so maybe some people can be interested. This is an example of an input for ADF for the excitation of 2p electrons in titanium tetrachloride. So this is the input. So this is the geometry, the symmetry, the exchange correlation potential. So you see this part is interesting. So you have the excitation part. So it means that we want to obtain 12 T2 excitation, which are the only one which are actually dipole allowed. And we are only interested in singlets because also this they are spin allowed. And actually, this is like in the valence, but for the core, since we are interested in core excitation, we have also this block. You see, modify excitation block, and then you can select the use occupied. So this keyword means that you use this occupied orbitals, and actually the second T2 orbitals of titanium tetrachloride are actually the 2p core orbitals of titanium. So in this case, we actually are doing the core excitation of the titanium 2p, and the results correspond to the pictures I have shown before. Okay, so this is the description of the method. Now, actually, there are also other important contributions, for example, relativistic effects, especially in the core region of the 2p excitation. We have the splitting of the spin orbit between 2p 1/2 and 2p 3/2 manifolds. So this is correspond to L2 and D to L3 edges. And for example, for titanium 2p, we have also calculated the same with the DORA implementation, which is available in ADF with the spin orbit. And we see that in the experiment, the splitting of this core orbital is 6.1 eV, and the calculated is 5.85, so in very good agreement with respect to the experimental value. This is the same spectrum of titanium chloride. This is actually another experiment, more recent, that we have done at the synchrotron here at Trieste. And this is the comparison with the calculation with the ADF, which also include the spin orbit coupling. So you see that these were the two bands that we have analyzed in the previous non-relativistic scheme. Now we have the complete relativistic scheme with, so we have both edges. This is the coupling of the spin orbit, and we see that also all this splitting is a very good agreement with respect to the experiment. So there are also other features which are attributed to Rydberg orbitals, which are, I mean, less important, but I want to show you that we have a really good agreement between our calculations with respect to very accurate gas phase experiment, which are, I mean, done at the experiment. Also, this is published by us many years ago. Okay, some more problematic problems are when the compounds are less ionic, because you know titanium tetrachloride is a rather ionic. The electronegative of chlorine is very important, so the covalent bonds are strongly polarized. We have seen that when we have more covalent situation, the accuracy of the results is less less satisfactory. For example, in ferrocene, which is iron bis cyclopentadienyl, and for example, we have seen that in that case, okay, I will go to this result. In that case, it is more important to have to use, for example, hybrid functional like B3LYP, which are not very efficient in ADF, but they have been implemented, so it is possible actually to do this also for ADF. So what I want to show you is that there are these ferrocene have been substituted with different ligands. For example, here we have vinyl ferrocene, echinyl ferrocene, and ethyl ferrocene, and you see that we have this part of the spectrum which is very sensitive to this substitution, and this part is very hard to be described, but using this B3LYP, we have been able actually to describe very accurately this part. So this effect, which is a very teeny effect in the experiment, can be very well reproduced by calculation, and of course also given the interpretation of this feature, which is of course connected with the ligands and actually a kind of conjugation effect between the double or triple bond of this substituent with the rings of the sandwich compound. Okay, now we have also done some application to phthalocyanine, for example, in this case with TDDFT on the, for example, K-edge, and on nitrogen, for example. Okay, and this was an example. But I want the last argument that I want to show is about the calculation that we can do about the NEXAFS spectra of molecules which are absorbed on surfaces, and in particular because when the molecule is absorbed on the surface, we can also study the polarization dependence, because the intensity of the radiation, so you see here the usual transition moment with the initial state and final state, and here we have the field polarization. Then if we change the direction of the polarization of the light, we can register different spectra. And this is very sensitive, of course, to the orientation of the molecule, the surface, so we can infer the geometry of absorption of the molecules. Of course, when we treat adsorbed molecules on surfaces, it is not an easy task. So actually we have, I mean, a rather complex protocol for calculation. So we start with a periodic calculation with another code, actually with the quantum espresso, with the periodic calculation with a superset. So when we have calculated the absorbed molecule with this periodic calculation, we cut a finite cluster, and we check that the electronic structure of the cluster is in good agreement with the periodic calculation, for example, checking the molecular orbitals of the DOS, for example. Then, when we are happy with the cluster model, of course, we can calculate spectroscopy with a molecular approach, because actually we are calculating a cluster, so everything that I have shown before can be also applied with this method. So in this case, we have done various applications. I will show one example, which is the absorption of ethylene on silicon 100 surface. And we have in the literature, there are these NEXAFS spectra which are calculated using different light polarization. Actually, we know that on the surface of the silicon surface there can be two different geometry of absorption, and so we can compare the spectra which are calculated in the two geometries with respect to the experiment. So, for example, this is a on-top absorption of the molecule on the surface, on the silicon surface, and we have three different polarization. You see, this is these are the axes, so you see these are the three possible polarizations. So you see that actually the agreement is rather good, because you see actually, of course, there are some discrepancy, but actually we have a good agreement with respect to main features. So you see also here we have some absorption here, and also here. So it seems that with this geometry, the calculated spectrum is in good agreement with the experiment. So we think that this on-top absorption seems to be rather reasonable. On the other hand, if we assume this other geometry, which is a bridge absorption, which is also, I mean, a reasonable absorption site, we see that in that case the calculation, the calculated spectrum is is no more in agreement with the experimental spectrum. So from this information, we are led to rule out this kind of absorption. But of course, because we have a computational tool which allow us to compare the absorption geometry with respect to an experiment. Okay, then we have more recent application with the aminobenzene over gold surface. So also here we have different spectra with respect to different light polarization. Also in this case, we are happy with the description of the spectrum using this method. And okay, this was the last example. And just to conclude, okay, we have seen that for metal L23 edge TDDFT is good, but if we need to consider K edge or in general K edge of metal or ligands, we can use also DFT with the Slater scheme. And of course, now we are interested even on larger schemes, for example, for TDDFT, or even with the new algorithm. Okay, so this is the, of course, and we do application with many colleagues. This is our group in Trieste. Then I have a close collaboration with people in Pisa, and of course with the synchrotron, and of course with respect with SCM for all the stuff about ADF. So thank you to everybody very much for your kind attention. Now I think I can, sorry, to reply to your questions, I hope.
Yeah, thank you, Mauro, for such an interesting presentation. And indeed, if anyone has questions, please feel free to type them in the chat box. Yeah, please, go ahead. Mauro?
I see.
I guess you can also see them, right, in the chat box?
Yeah, I see.
Okay.
So, okay, so Hossein is asking about the new algorithm, if it is less efficient. I mean, it is, I don't know, of course, it depends with respect to what, because the problem is that if you have a large metal cluster, you cannot treat it with the Davidson algorithm, because you would need too many eigenvalues. And if you try to extract too many eigenvalues from with the Davidson algorithm, at a certain point the algorithm is no more stable from the numerical point of view. So actually, even if you have a larger computer, it doesn't work at all, because the algorithm is not suited to extract too many eigenvalues. So this is a bottleneck. So in this case, the new algorithm is more efficient, because maybe, I mean, usually with the same computational effort, you can obtain a very wide energy spectrum. So in this respect, it works properly. You don't have any numerical problem, even if you go to higher energy. Okay, no, I hope that okay, I hope I have explained. So if you have more questions in this respect, ask me more. So the second question was about the Slater method. Yeah, of course, in the Slater method, the original formulation is that you calculate a electron configuration when taking only half an electron from the initial orbital and you put it in the virtual orbital. Of course, you can say, what does it mean for half an electron? Because I mean, if you go in the very old Slater book, actually he did a kind of total energy Taylor expansion with respect to the occupation number. So if you start with this transition state configuration, you can show that at this point the excitation energy is correct up to an error in the third order. So this is the reason. So you have to do this Taylor series, and then from that series you understand why this strange configuration has been suggested by with these strange occupation numbers, from fractional occupation number. Of course, you can do by ADF, because in ADF you have the occupation keyword, and then with playing with the occupation, you can also calculate this Slater configuration. Then there is another question from science that then it works for main peaks. Of course, it works for main peaks. Actually, it does not work for satellites, if you mean, because probably maybe Hossein means that you do the difference between main lines and satellites. In that case, actually, to describe satellites, it is for the first questions, of course, for the Plasmon. But satellites are very hard to be described at TDDFT. So usually for Plasmos is not a satellite in this respect. Maybe we have different because I mean the problem of what we are speaking about is because I am a chemist, so maybe solid state physics maybe have a different vision about the Plasmon. For me, a Plasmon is a strong collective excitation which is contributed by many configurations. But this doesn't mean that this is a satellite, because a satellite for me is a different phenomenon, which is related with the fact that after you ionize a system, the ionic fragment then is not in his ground state, but it is an excited state. So for me, I have this. For this kind of satellites, TDDFT is not enough. You have to go to some more ab initio. Then there is another question from Alfredo that sorry, that I have to check. Okay. Well, this is not an easy question, because when you choose the functional, of course, the functional actually play two roles. One role is in the description of the electronic structure of the systems, and then also in the optical part of the system. So actually, it is not easy to decouple the problems. So I think that when you have an organic molecule, the best would be to take a well-known example of a simple molecule, and then to test on with respect to a sure experiment. What I think is, because you mentioned dispersion correction, so maybe the dispersion is very important for the total energy, or for example for your probably geometry optimization if you have to optimize it. So a good strategy could be, of course, I don't know your problem, so it is just a suggestion, you should check it, is calculate first your geometry or your energy with your dispersed correct the functional, and then you take that fixed geometry, and then you do a TDDFT calculation, but with the functional with the correct asymptotic behavior, and then maybe you have some, I mean, sensitivity about the requirements with respect to the functional.
And there is another question from this HTML5 viewer user.
Okay. Well, okay. We usually employ it for closed shell systems. Actually, there are some extensions to open shell as the TDDFT, but I am very cautious in this respect because let me explain. There are these multiplet effects which are very important, and which for open shell systems your ground state should be described by many determinants. Of course, in this respect, TDDFT is not good. So, I mean, technically, it is possible to calculate open shell systems, but I would be very cautious. I mean, there are also in the literature some examples. So, in that case, I think you can do, but you must be cautious. So I don't say that open shell cannot be calculated, but it is not, the implementation works, but there is this fundamental problem of TDDFT that you have problem if the ground state should be described by many determinants, because this is not possible.
Okay.
Okay, you are welcome.
So I think there are no remaining questions. If there are any, please type them or type something. Otherwise, I would like to thank again Mauro, Professor Stener, for putting together such an interesting presentation and for taking the time to answer questions. I think we can finish now.
Okay, so thank you very much to everybody. I was happy that there are so many people interested in this. And of course, should you have some more questions, you can write me an email. So I think there is an email on the first slide, so no problem. So do not hesitate to contact me if you have more technical or other questions.
Indeed. And as I mentioned before, we'll be making the slides and the recording available. We'll share the link with you. And well, I think that's it. So I wish you all a nice, well, a good morning, evening, afternoon, wherever you are now. And thank you again, Mauro, for all your time.
Thank you. Thank you. Bye-bye.
Thank you. Bye.
Bye-bye.